Well, everybody, welcome to Jim's Friday night e-day, e-learning day, I should say. I hope everybody's safe. I wanted to talk a little bit more about the Snake Lemma, where we left off earlier in last class. If you remember, we have the following commutative diagram of R module homomorphisms with the exact rows. Then we get an exact sequence like this. There was also in the Snake Lemma, which I didn't add here, but there's another caveat. There's kind of an extra bonus that if F1 is 1 to 1, then this alpha 1 will be 1 to 1. And also if H2 is on 2, then the last map beta 2 is on 2. But I'm not going to go through a tedious proof of this, but I hope talk you through it a little bit. The biggest thing is the snake, which actually goes from the kernel of G, which is, kernel of G3, which is up here, into the co-kernel here, B1 mod, the image of G1. But here, so for example, how does this work? Let me just give you an example here. Take an element alpha 1. Let X be in the kernel of G1. So that's something that I can say for it. And really what alpha 1 is just induced by F. Just whatever F1 is. It's really a different map because you've got a potentially restricted domain. Now, why is this in the kernel of G2? Well, if you have X and it's in the kernel of G1, it has to go to 0 there. So when you push this, F1 of X, which is our alpha X, the diagram must commute. And so whatever goes to down here is the image of 0, but since it's the image of 0, this has to be 0. So in other words, what we're saying is F1 of X is actually in the kernel of G2, which is exactly what we wanted. So this verifies this map is where we want it to be. Notice it's fairly easy that this is that the composition of alpha 1 and alpha 2 is 0 because the composition of F1 and F2 is 0, right? And showing that the kernel of this is contained in the image of this is not too difficult at all. There's similar stuff for the co-kernel. It's always because you're going from actually A1 to these images, or I'm sorry, B1, not the images, or BI, not the images, I should say. But I want to focus on the snake. I'm not going to prove this is a homomorphism. I'll leave that to you because, but I just want to give you a feel for how this little miracle works. So how does a snake work? Sometimes people write it this way. Get this because I'm gonna need some drawing room. It's often written. So if you start with A3 here, and what you know is A3 is in the kernel of G3, so it goes to 0 in B3. This is often written this way. Delta of A3, or this snake homomorphism, is F2 inverse A3. And of course, you should already be foaming at the mouth, right? Because this function, there's no reason to think that it's invertible. In fact, it's not. So think of that really as a pre-image. And of course, then the next complaint, justifiably so, will be, oh my God, but this map looks like it's onto, so the pre-image could be this entire infinite set. Yes, it could, but just go with me for a moment. Then you apply G2 to it, gets it down here, and then H1 inverse. And that thing's got That's got more problems than Carter's got pills, right? I mean, there's all kinds of problems with this. But let me kind of talk you through what's going on. Why does this actually work? Why does this actually, the first question to ask, which, I mean, what I really want to address is, why does this give you something that's well defined? Well, so you start with A3 and you take some element that goes to it, A2. And of course, we're already in trouble, because let me at least acknowledge the fact that there could be more than one that goes to A3, and that's really kind of the problem. But nonetheless, we'll push this forward to, we'll call this B2, and we'll call this B2 prime. Right? These are two different choices I might have made. Now, notice that the diagram commutes, right? And since A3 was in the kernel, both B2 and B2 prime must go to 0. So in particular, both B2 and B2 prime have pre-images in B1. And this one is a little bit better. The H1 inverse is a little bit better of a situation, because H1 is actually 1-to-1. So once you acknowledge that B2, say, has a pre-image here, it has to be unique. There's only one of them, because H1 is 1-to-1. It doesn't have this mess that this does, but still, it seems like really kind of flaky. So here we have B1, it goes to B2, and B1 prime going to B2 as well. All right? So I could have followed the yellow brick road. I could have followed the red brick road, which I always wondered where that one went. But here it's going to be a well-defined choice. And let me show you why. A2 and A2 prime both go to the same animal over here. So their difference goes to 0. So there exists, call it X. X in A1 that goes to A2 minus A2 prime. And notice this will go to B2 minus B2 prime, because A2 goes to B2 and A2 prime goes to B2 prime. And of course, X folds this way, and I'll call this G of X, just to keep, because it's going to be useful for me to keep the G notation here. The G1X. Now, again, I want you to notice that G1X has to go over here to, see, X goes this way to B1 minus B2. I'm sorry, B2 minus B2 prime. This has to go to the same place that A2 minus A2 prime go. Right? Now notice that what this means is, notice that, right. So if you look at B1 and B2, look at what happens under H1. B1 minus B1 prime goes to B2 minus B2 prime. Right? So B1 goes to B2, B1 prime goes to B2 prime. So the difference of these two goes to the difference of those two. Also, G1 of X also goes to B2 minus B2 prime. Well, notice that H1 is 1 to 1. And since H1 is 1 to 1, and G1 of X goes to the same place that B1 minus B1 prime goes to, this means B1 minus B1 prime is equal to G of X. And after all this work, this is amazing. G1 of X is in the co-kernel, is in the image of G1. So the difference between B and B1, the two choices that I could have made, given my different choices here, their difference is in the image of G1. And this means that the coset B1 plus image of G1 is equal to B1 prime plus image of G1. So the coset B1 plus image of G1 coincides with B1 prime plus image G1 in the co-kernel of G1, which is B mod M G1. So after all that, what that means is if A3 is in the kernel, no matter what choice I make, I might get different B1s, but they vary by something in the image of G1. So they give you the same coset in the co-kernel of G1. Now, that's far from proving that this is a homomorphism, but actually going through the motions to show this is a homomorphism is more routine than what we just did. Exactness is another barrel of laughs too, but I'm not going to get that much in the weeds in this class on this, unless you are a weed lover, in which case you would, I probably shouldn't say that, in which case you should probably come see me and we'll talk about the weeds, these kind of weeds, not the illegal kind. So here's one of my favorite theorems. Theorem 12.4.8. And I'm gonna take some care, unlike my little wavy hand stuff with the snake lemma, just to kind of get you all on the playing field. I'm gonna take a little bit more care here with this one. Suppose R is a ring and we have a short exact sequence of R module homomorphisms. 0, A, B, C, 0. I want this to be a short exact sequence of R module homomorphisms. R module homomorphisms. Following conditions are equivalent. TFAE 1, there exists an R module homomorphism. Here my letters will all be R module homomorphism from C to B, such that when I do H and then I do G, this is the identity on C. Number 2, there exists F from A to B. Oh, I'm sorry, already there. There exists K from B to A, such that when I do F, then I do K, I get the identity function on A. And finally, the sequence above is isomorphic to the sequence uh, zero, A direct sum C, C, zero. This is inclusion in A, and this is ejection on C. Where I'll make this clear, inclusion A of A equals A comma 0, and pi of A comma C, C. In particular, B is isomorphic to the direct sum of A and C. Okay, now I did leave one thing out here, and that is, what do I mean by isomorphic sequence? So in the statement of C, we can define a commutative diagram that looks like this. Zero, G, 0, A sum C, C, 0. This is the identity on A. This is the A, pi C, identity on C, and some magic function here. This is what I mean by there's an isomorphism of sequences. There's a commutative diagram that looks like this. The original sequence, this nice special sequence. Now, such a sequence, such a short exact sequence is called a split exact sequence. This is called a split exact sequence, which is like a short exact sequence on steroids. It's just kind of a much stronger version. And I want to take it. Anyway, so it's a stronger version than the ordinary short exact sequence. We've seen some short exact sequences that definitely aren't split exact. We saw Z2, Z4, and Z2, and there's no way that splits because Z4 is not the direct sum of the two ends. Let me also point out that if the sequence splits, then the middle is the direct sum of the other two. The converse is not always true. You can have short exact sequences where the middle is the direct sum of the ends, but you don't have these maps here. You don't have these. By the way, the maps H and K in here are sometimes called splittings. So a split exact sequence is one that essentially can be run in reverse, right? It doesn't matter whether you start A or C, you can revamp it and start with C. Okay, so I think the big thing I want to do is try to show you why this business all holds together for us. Right. So the first implication I want to do, let's do A implies B, or 1 implies 2, I guess. And how we're going to do that. So we've got the splitting here. F, G, and we've got this animal that goes back here, H, and when I do G, when I do H first and G, I get the identity on C. Now, how am I going to construct a K? So now, big question is, what's an intelligent way to start with a B in here and get over here, right? I mean, I don't know that I can, if it's already in the image, that's what I'm tempted to do. If B happens to be in the image of A, then I'm tempted to just pull it back. But of course, this is usually much bigger than A, one would expect, because this map is just 1-to-1. So if I have a garden variety B, how do I associate it with something back in A? And I call this sort of cleaning B. So consider let's do G of B and then H. Take B and run it through the washing machine. Apply G to it and then bring it back with H. Now, how does that help? Well, it helps in the following way, because what I'm going to do now is notice that G of B minus HG of B. So we take B, then when I run it through the washing machine, this is my new improved B. Look at the difference between B and my new improved B. If I apply G to it, this is GHGB. But remember, when you do GH, this is the identity. So this is G of B minus G of B, which is 0. And this gives me an intelligent way to assign an A to it. B minus HGB is in the kernel of F, which is, the kernel of G, which is the image of F. And so there exists some A such that F of A is this thing. So I'm going to define K of B and let me point out that this is a pre-image. But remember, F is 1-to-1, and so the pre-image is unique, right? So there's no ambiguity here. This is a well-defined input B. This thing has a unique pre-image in A, and that's what I'm going to call that thing. Now suppose F inverse of, now let's suppose that F inverse of B1 minus HB1 is A1. And F inverse of B2 minus HG B2 is equal to A2. Now I'm going to apply F to this. Notice that F of A1 plus A2 is equal to B1 plus B2 minus HG B1 plus B2. Because everything here is a homomorphism, right? So I did that homomorphism with the HG pretty quick, but they both compose into homomorphisms. So we have that K of B1 plus B2 so K of B1 plus B2 is equal to F inverse of this mass minus Hg B1 plus B2, which equals F inverse F of A1 plus A2, which is A1 plus A2. And of course, this is K of B1 plus K of B2. So there, this is a homomorphism of the abelian part. I'll let you do the one, show that the scalars pull out. That's pretty routine to do. And so notice that also notice that when I do, let's see, when I do F and then I do K of A, well, this is by definition F inverse of F of A minus HG F of A. Let me check to make sure that I got that right. F inverse of HG, yeah. And notice GF is the zero map because this is the composition F and G. This original sequence is exact. So this part is gone. This is F inverse F of A, which is A. So there you go. We've got our F, and it's a right, and it's a R modular homomorphism. Let's do B implies C. Let me kind of give you some details here. Let's do 2 implies 3. For that one, so let's do this. So we have 0, A, B, C, 0. This is my F and G. And for this part, I know I've got my K. It goes back here. And when I do F, and then I do K, see identity on A. All right, so the first thing I want to do is I want to find my phi. And in this case, I want it to go from B to A sum C. And how am I going to do that? Well, I'm going to do what I think the most natural thing I think to do. I'm just going to use G and K to generate what I need. So it should be K of B. That should give me my A coordinate, and G of C, I'm sorry, G of B should give me my C coordinate. Now, this is easily seen to be an R-module homomorphism. Because basically it's an R-module homomorphism on both coordinates. Notice that phi B1 plus R B2 is K B1 plus R B2, comma G of B1 plus R B2. Break these homomorphisms up within the box. This is K B1 plus R K B2, comma G B1 plus R G B2. And now let's split this up sagaciously. K B1 G B1 plus R K B2 G B2. That looks right to me. And so this is phi of B1 plus R phi B2. Yay, it's an R-module homomorphism. How about 1-to-1 and onto? Let's do 1-to-1 first. Run our chalk here. Let B be in the kernel thing. This means that KB equals right. So this immediately gives me implies B is an internal of G, which is the image graph. So there exists an A and A such that F of A equals B. But now we have the equation KB equals 0. So let's use this part of what's going on. But I know that B is F of A, right? And I know that KF is the identity of A. So this is A. Therefore, A is equal to 0, which implies F of A. So B equals 0, and this homomorphism is in fact 1-to-1. So here, now we'll show it's onto, and you'll see when I do this that this came from me sitting down beforehand, putting a little bit of blood, sweat, and tears. But at the end of the day, it's just solving some equation, just like writing down what you need to get, doing a little almost linear algebra with it. So let's let AC so just pick an arbitrary element of A direct sum C. Since G is onto, you can certainly say there exists B and B such that C is equal to G of B. Right? But I certainly don't know that the K of B is going to match the A. I don't know that. And so what I got to do is I've got to adjust this a little bit. K of B may not be A. So adjust. And how am I going to adjust? I'm going to adjust it by something that's in the kernel. So I'm going to vary this by an element in the kernel of G, which is the image of F. So instead of taking B, I'm going to choose B minus FKB plus FA. This is something that I'm varying by the, so basically, notice that this is leading with it. So this is in the image of F, right? This part here. So when I get this with a G, I'm gonna still get my same C equals G of B, but that she's gonna kill this part. This is designed, so whether I use B and apply G to it, or whether I use this big thing and apply G to it, the G is going to kill these two in the homomorphism. FG is 0. So it's gone. So why did I pick this? It's because it's what helps me to adjust with the F. And let me show you what I mean. First of all, first detail, G of B minus F A B plus F of A is equal to G of B minus G F A B plus G F A, which is G of B, which is C. So in my second coordinate, I get exactly what I need to get. I get the G of B as C. And the first coordinate, here's the fun part. F of B minus FK B. Oh, you know what? I think I typoed that. I looked, it's supposed to be. Oh, no, I did do that right. What I did right here is wrong here. So now we'll stick, it's not into the F, but into K. That's right, it's K of B, not F of B. So K of B, FKB plus FA. Well, let's see what we get here. This is KB. That's KFA of B plus KFA. Now remember, when you see a KF like that, it's the identity of A. And this is the identity of A. So this is KB minus KB plus A, which is A. So that gives me the second coordinate that I want. Okay. I am, and I really encourage you to do this. So the last one that we've left is C. So you've got the isomorphism. I'll sketch this one. So here's what you have. G F. I encourage this for kind of good practice. This is the identity of C, the identity of A, and this is phi. So in other words, we've got this. Oh, by the way, all I did in the previous proof is I should be careful, as I showed that there was an isomorphism from here to here. See if you can fill in the dots about why this diagram commutes. But that it's pretty straightforward. For the last one, what you need is you need to get this splitting map that goes here. So you need to find A from C to B such that when you do H, and then you do G, you get the identity on C. And how would you do that, you think? How would you go from C to here? Well, try this. I want to go from here to here, so let's just follow this diagram. This essentially does nothing, it's the identity. And then I want to get to B, so I'm going to go back here. So let's call this inclusion C. Start here with what do we call it? X. So X, do the inclusion here, and then phi inverse. And see if that doesn't make that diagram commute, right? And here, the inclusion of X is, now you're including in C instead of in X, okay? So see if you can make this work, compose this with G, and see if it works out for you. And it should. Okay, so I've wrapped up kind of what I want to talk about the snake lemma, and went through this business about the split exact sequences. Remember, just because if you have a split exact sequence, that means that the middle is isomorphic to the bookends, but that's not sufficient. You actually do need those maps that bow out in the other direction and compose the identity. Okay, everybody, be safe over this strange weather, and we will see you soon.